Okay, and so now we are all ready to calculate the actual value for the correlation coefficient. And so now, as far as calculating this, starting out by doing it by hand, or just going through a formula, then this is what we need for here. So to calculate this by hand, you first need to obtain and let's say your x data, in this data we've learned is called the x data, and then the data list y right here. We need to obtain the mean on the x list, so lowercase x bar right there is the mean value as we've been knowing it. And then we also need to obtain the mean value on the y list. So here I'm using lowercase y, but now with a bar. So famously in stats, bar represents the mean value, the average value. And then aside from these two values right here, we also need to find the standard deviation. But standard deviation on the x list, now we need to carry the symbol sx right here. And as well as we need to obtain the standard deviation from the y list. And our calculator, the stats button that we've learned a little while ago, can actually help us to handle this, pulling out these values without too much calculation required for us right there. So let me quickly show you how we can get it done on the computer screen here. But let's say, well, let me go back to the home screen right here. So once you're on your home screen, and you can click on the stats button in case you still haven't entered your data into the calculator. Spend some time doing that. But here I just want to show you that. So right here in my edit submenu, and I would like to go into the and double check my data that I have entered. So in my calculator here, I put the x data in my list L2 here of the calculator, and I put my y data in the list L3 of my calculator. And that's just a way to double check. And when you're doing this completely on your own, you have your choice of using other empty list or even start out with list 1 right here. And so now once you have the data successfully entered, we're going to use there's a convenient feature that we're going to use the command that says two variable stats. And this command right here is going to simultaneously bring up the value of all the x bar, y bar, sx, and yx, sx, and sy right here, all in one button. And so all I need is, once again, navigate to the calculation submenu after you hit stats button, and then select option number 2, which this time says two variable stats. I am going to select that command. And then now we need to indicate if your where you put your x data. So the x list here, I put that in my L2 list actually. So I'm going to go second 2 on the keypad, and so that will brings up the list L2 being indicated. Then I'll hit enter, and then I'll hit second 3 for retrieving list L3 to be my y list. And now I'm going to hit enter a couple more times. And so now at this blinking cursor highlighting the calculate option right here, I'm going to hit enter one last time right here. And the calculator will immediately give me the value for all of these, the values that we need. So x bar is here, 9.4285, and a lot longer and a lot longer. So in our lecture here, we only need to use 2 decimals. And that's good enough for the demonstration purpose here. So 9.43 rounded to 2 decimals is what we need. And then Sx, in this case, your calculator is giving, and like I said again, we will never use the sigma symbol down here, so completely disregard that. I'll just use the Sx right here being 3.5989 and all that. So in 2 decimals, we have no choice but just staying with 3.6 right there. That's about the best we can go. And then how do I find the y data? You see, we can use the up and down arrow key right here, and to start navigating down further on the list, and it start switching over to the y list. And so starting with your y list, the center of the data, the mean value is here. So the y bar, according to our calculator, provided that you did not make any error in entering your data. And so our data here is having y bar being 0.67, and like I said, a lot of time I commonly round to 2 decimals. Every assignment, every problem that you're doing is having a different rounding requirements out there. And then sy in our need tree here, the calculator says 0.14. All right, so now that's good for us here. So calculating the OR coefficient. Now, the famous n number I used to talk about back in the days that we talked about the data 1 or the small data list. N number is how many data values in the list. But here, since we have 2 sets of data, and they go to, as a pair x have to go with a designated y value after we record the data. So n number in our dual data like this is simply referred to the number of pairs. And so for our data in this current problem that I'm doing, we got n equals 7. We got 7 pairs. That's a brief explanation of that. All right, and so now actually getting into the calculation, here's how we can calculate our correlation coefficient here. That value r is going to be found by, and then eventually, as we are now all living in the 21st century, I'm just showing how to calculate the correlation coefficient using the formula here, but that's just maybe once or twice we have to do that, and in the lecture for you to understand what's going on here, but eventually we are going to move toward that way of letting a calculator to handle this calculation, which is a lot faster and more effective. So the correlation coefficient we're calculating here, if we are using the formula, then I'm going to go 1 over, and here my number of pairs 7 minus 1. So that's the number of pairs minus 1. So eventually it's going to give me a 6. And then in the denominator, I'm going to multiply with 3.6. And then as I'm writing down my formula right here, then you can start recognizing what are these values in the formula, so that eventually we can, so that at the end we're going to formulate the actual formula here. And then we're going to also multiply in the denominator as well. Okay, 0.14. Okay, and then let me readjust my 1 right here to make the fraction looks a little more appropriate. So 1 over the number of pairs minus 1 in product with 3.6 in product with 0.14, all of that product here in the denominator. Then I'm going to open up a large square bracket right here. I'm going to go back to my first pair of data. So the first pair of data here on my screen shows 5 for x and 0.45 for y. So this is what I'm doing in my formula. I'm going to have 5, the x value of the first pair, minus 9.43, and then that's difference there between my x value, my first x value, and the mean value on the x list right here. And I hope you're now starting to recognize that 9.43 is the mean value on my x list. I am going to multiply that difference there with 0.45 minus 0.67. So once again, before we move on to the next data value, then 0.65 is my first y value, and here 0.67 is the mean on the y list. So what I did here was that for each pair of values, it looked like I subtract the mean value on the corresponding list from the first value of the same list right here. So the mean value on the y list being subtracted from the first entry, okay, and multiply the two differences together. So that means, and then after doing that, I am going to move on to my second pair. My second pair says x values being 6, and I'm subtracting the mean repeatedly, 0.43, and then the y value correspondingly there, I am going to, well, that's y value 6.62. I am going to subtract 0.67. So you can start recognizing some repeated work here being applied on different pairs of value here. So each pair I'm going to go with value minus the mean, value minus the mean here, and then I'm running out of line a little bit. So supposedly this calculation, this adding up work is continuing until the rest of the data. And so I'm going to add, so what I'm doing, continuing to write here is to be completely contained inside the brackets there actually. So I'm going to add to my next pair of values, being the x list. The third value on the x list is 8 minus 9.43, and then the y value on the third entry is 0.65 minus 0.67. Okay, so 3 times I have done that, and so I will keep doing this and repeat doing this until I hit the end of my data. And so, well, luckily this example here, this little small problem here is only 7 pairs of data. I mean, imagine before these calculators were born, then how statisticians have to carry through all of this work here. So I'm going to continue doing that. That's what the dots here represent, and I'm going to continue doing that until the end of my list. My last data value on the list, x, was 15. I'm subtracting 9.43, and the y value there was 0.85. I'm subtracting 0.67. Okay, and then here I'm closing my brackets. And so that completes my formula. So the calculations will turn out to be, and of course, you can pause the video and spend some time start doing this and see how much time it takes you, it costs you for doing this. So the calculation shows that I calculated 0.85744, and usually when it comes to this, I tend to go a little further than 2 decimals. So say 5 decimals here is the case. Okay, and so, and I need to make a note that before I proceed into calculating this correlation coefficient here, my live example over here, I was actually going back to the data I showed you, but before the correction, because remember I was doing a quick little demonstration that we made some updates in a couple entries so that I can show that scatter point came closer to the line. But this calculation came out from the original one, the initial one that I brought up when the scatter point was still big and the scatter region was still big. And so what's going on in this formula was that you can see, so let's have a look one by one pieces here, piece by piece here. But so we got a square brackets here, and inside each of these we have, so it looks like we have in that square brackets, it looks like what we have there, and I'm writing down this general formula here. It has an intention that when you actually have to, in a position that you have to go through the formula and doing that, doing the adding work would be a better decision to get your work done a little more safely. But each of the subtraction here in the products there, it seems like it's the value x1 from my x list. Subtract the mean, multiply with value y1, subtract the mean on the y list. And so that looks like what happened in my first product right there. And then we add, and then it looks like the next one here was my x2 in the data, and subtract the mean on the x list times in product with my y2 minus the mean on the y list. And it looks like I repeated this until I hit the end of the list here, being the last data value, namely xn again. This is for the end pair value, so the xn at the end pair minus the mean on the x list times y at the last pair minus the mean on the y list. So it would be better that we add up all the products of the differences between values and mean on each individual entry right there. So value minus mean, take the product. Next value minus mean on the y list, take the product, and add up all of those pairwise products until the end of the list right here. And after we're done, we're going to multiply that sum by a fraction 1 over So let's look back into what we actually did in our work right here. But 7 here is the number of pairs minus 1. So in my fraction that I put in front of the brackets here, it was supposedly the n minus 1, like that. The number of pairs minus 1 times 3.6 was indeed your Sx value, and 0.14 was your Sy value. So this actually completes our formula for calculating the correlation coefficient. So R equals with all this here. But so calculating R using the formula eventually become disadvantage actually, because the formula is correct. But what happens now is that right inside of each of these values, the standard deviations and for each from the standard deviation from each of your list and the mean value, we all have to round it quite extremely already. And so there are a lot of times there are times where we need to have more precise than that. And the bigger disadvantage is that it's long. The formula is way too long, and it created a high risk of making errors when you're typing in your calculator and to do the work. And so I keep telling my students a real story, that there are a couple times, a couple quarters when I'm teaching a stats and the exact same problem when I brought up, but this answer here I run into 10 different answers right there, simply due to the fact that if we really carry through the calculation here, it's just way too risky in the fact that typing out the typos can happen all over. And so sooner we're gonna, very soon we're gonna turn over to use a calculator, and you can learn that one quick button can get that value here, and in a much more precise version. Here, this value here is of course still not that precise, not that accurate, because we already have a lot of rounding going on in each of these values. So getting anywhere to this value right here was already a pretty lucky and good answer. But now, before I turn away, and then let's have a look right here. But so our data that we've seen on the Microsoft Excel screen, we already saw the scatter plot, and it was an uptrend, a rising trend right here, and it was so-called positive correlation. So that was what's really happening in our data. And so let's look at the R value here. And once again, now I just want to reinforce our correlation value being positive. And that explains for our scatter plot was showing a positive trend, a rising trend. So now let me take things in a slightly off direction a little bit, but let me kind of branch out and show everybody how to use the calculator, your standard TI 83 or 84 to do the calculation of the correlation coefficient. And so once again, provided you already enter your data, and we can always double check by enter the edit submenu and go to edit, the first entry. And once you have ensured that the data is all being there and properly entered, well, typo free is your only responsibility for entering your data into the list here. Before we can actually proceed with calculating the correlation coefficient, we actually need to do this, turn on a feature right here. So I'm going to go to second 0, which brings up the catalog menu of your calculation, catalog menu of your TI calculator. We're going to use the down arrow key to scroll down until we reach to the, and you can see that all the catalog here brings up the whole comprehensive list of all the features, functions, and features of your calculator. So keep scrolling down, and these features and commands are here. They are being ordered in alphabetical order. So just keep scrolling down. And so now once you have scrolled down to those commands with the letter D's right here, then we're gonna look for that command that says diagnostic on. So I repeat, it's diagnostic on. And so right now, once that little arrow is pointing to diagnostic on right here, you're gonna hit enter on your keypad. And right now on your home screen, you see nothing but except just the command being printed, and then with a blinking cursor, we want to hit enter one more time. And seems like nothing was done except for there's a word done being printed here, but that's indicating that the feature has been turned on. Now, so before I start using it, just want to make a note here that for this calculator of yours is designed in a way that once you turn on that diagnostic on feature right here, it will stay on permanently unless you turn it off. And I hope you noticed earlier there was if I hit the second 0 for bringing this up the catalog again. Well, I don't want to go through the whole scrolling down again, but there will be a diagnostic off right next to diagnostic on right there, unless you want to turn it off. But like I said again, well, once you turn it on, it stays on. But even if it stays on, it never hurts to the double turn on. Meaning, maybe get for yourself into a good habit that any time before you run this analysis on the data on the correlation coefficient, always make sure that you hit the diagnostic on before you're done, regardless it has turned on or not. But now after you turn on the diagnostic on feature over here, we're gonna hit the stats button. We're gonna turn over to the calculation menu. This time I'm scrolling down to line number 4 that says LinReg. So LinReg short for linear regressions. So now I'm gonna hit enter. And so once again the calculator is asking for where do you put your X list, and here I'm putting my X list in L2, so it's properly addressed here. And then I'm putting my Y list in L3, so I'm hitting enter to navigate down to L3. And so after double checking that it has my list there indicated properly, now I'm gonna just hit enter a couple more times to skip these other lines right here. And now we hit enter one more time to get down to calculate, and the last time we hit enter, the work is gonna start being done. So here's the result right here, and the value you are looking for is the last line right here, saying R equals 0.8442477, and so on and so on. And so it has a few other values, but I'm gonna wait until you have some more understanding, and then we're gonna come back and have understand what they are. But for my class, actually, for viewers out there, if you don't have the need of using formulas, then these are eventually I'm gonna explain that. But for students in my class, I expect you that you only use this command right here to find out your correlation coefficients. And then we're going to learn how to calculate these other values using the formula. And so now our correlation coefficient value, the really precise version, because of course the calculator is having a much stronger calculation power compared to us right here. But R here is in 5 decimal, usually that's what I go with, 0.84425. And it is slightly off from what we calculated earlier, but this is a lot more precise due to the fact that your calculator could take consideration of each of those X bar, Y bar, and SX and SY. The calculator went with all of those precise value in real good precision right there. And so a lot of time throughout most of our calculation work, I simply expect my student to know how to use the calculator to get that value instead of going through the formula. All right, so let's have a look again into our data. So we now using the powerful calculator, and we calculated that correlation coefficient was a 0.84425. And so in that way, once again, our data here, looking at the scatter plot, it was showing a rising trend, a positive correlation. And so now the calculation values is being 0.84425, and it is, again, that's we have R is being a positive value. And once again, it was no lie about R calculated after calculation came out being somewhere inside of this interval in between -1 and 1. And so now after we've done calculating the correlation coefficient, and I've shown you the two different techniques. Either you can use a formula or you can use the calculator. Then, so here's the thing. So the idea of the correlation coefficient now is that now you have your scatter plot forming into a rising trend or a positive correlation. And then the more it is, so this is R is greater than 0. And then, of course, if the data become even more closely lined up, then we refer to this as strongly positive. So the strongly version, strongly positive. And the value R here is closer to positive 1. And so just think about it like this. There are actually times where, well, in the end, these scatter points are scatter point, but who knows? Sometimes when you are so lucky that you looked at your data that's really meant to come out from a linear function. So there could be time that your scatter points are like that, where there is perfectly a line that runs through them. And so ideally speaking, data like that is when R equals exactly positive 1, because it's rising and it's perfectly on a line. And so now over time teaching, I keep having students mistaking that R is the slope of the line. It's not true. R is not the slope of the line. R is just to determine how close your point stays to a line like that. So in case where your point stay on a line like this, okay, the slope here is some slope. It could still be a rising slope, but in a much higher slope. You see what I'm saying? So slope can be a lot higher than 1 right here, but the correlation coefficient value can be the most. It's just positive 1. It's indicating that all points are on the line and being a positive slope line. So to clear it out, the misunderstanding, the misconception here is that the correlation coefficient is never going to be the slope. There are two different things. And so the idea about R equals positive 1 in theory happens, but it should stay quite theoretical there. It doesn't really happen in our stats work too much, because the idea here is that a lot of time when we observe data came out from scratch, just being scatter data, they are not expected to have any kind of relationship. And so it's more practical that we're looking at data that's bouncing up and down from that line right there. And then for the other case, when the data came into a falling trend, the scatter region is forming a falling trend here. If I accidentally said the rising, I apologize, but I meant the falling trend here. Then we call this the negative correlation. And similarly, it can become more strongly. Graphically speaking, it's forming into a thinner bandwidth, and we call this strongly negative correlation. And this is, both of these cases right here refer to when your correlation coefficient is negative. That's both negative, but in this case specifically, again, then your R value is closer to negative 1. And you see, like I said, I need back to what I said about R will never be the slope value, because see, in this case right here, the slope is eventually a negative slope, but it could be a very deeply falling slope, but the lowest value for R can only ever get is negative 1. And so, along with what I just said right there, yes, there could be time where you have a line with a negative slope, and your points, your scatter points, are perfectly on that line right there. So that is where you have R equals negative 1 precisely, if that ever happens. But once again, I see this as just something that can theoretically happen, but in the work for statistics right here, it almost never happens. Okay, so And last thing before I'm moving away from calculating correlation coefficient, then there could be time too. There are times out there where your scatter plots are like this. The scatter regions, even when you're trying to circle and around your scatter regions, somebody see this as slightly going up, somebody can still see this as slightly going down. I see this as clueless. I cannot recognize a pattern at all for this. And so with a scatter plot like this, yes, through the eyes, we can say that we have an unclear pattern, or an unclear correlation. Okay, and so how is that correlation coefficient explaining for that? So remember, and you already have seen enough through the examples, correlation coefficient only exists inside of that interval between -1 and 1. And there are two extremes here, being closer to that. +1 means your line is going to be rising up, and then having points are closely lined up on a line, on that line with positive slope. If your R calculated to be closer to -1, then there's a negative slope line, and your points are more closely lined up on that negative slope line right there. But now when your R gets closer to 0, 0 is exactly in the middle. So when R is closer to 0, the closer to 0 is, the more dispersed out your scatter point is, and the more unclear in terms of the pattern. And so this situation, like right here, I'm going to say, as far as the R value, everything we know, all we know is R is closer to 0. I can't really say precisely, or precisely how precise that is. It all depends on, we have to tear it down to a real calculation. But here, it's just all I can say is, for something like this, the correlation coefficient, I'm sure it has to be closer to 0, because and it's unclear. We're not sure where exactly it's going.